Okay, so we move into chapter 6. We're going to talk more about areas. But in chapter 6, well, they mention here, and I can highlight it. In chapter 5, we defined and calculated areas of the, there, get a little bigger. In chapter 5, we defined and calculated areas of regions that lie under the graphs of functions. Here we use the integrals to find areas of more general regions. Okay, we're going to consider regions that lie between the graphs of two functions. So let's see what they're talking about here. Okay, so here in figure 1, you have an area S. And the area S, this is from section 6.1, figure 1. The area S is enclosed above and below by two functions. The top function is f of x, and the bottom function is g of x. So, up to now, the areas that you've been finding, up to now, the areas that you've been finding have been where you have a function on top, some function f, and then the x-axis is below, and you're finding the area between the function and that x-axis. But now we have a bottom function, g of x. So how would we go about finding this area? Well, so we can go back to the idea of a Riemann sum. So remember, when you learned about integration, you learned, okay, well, if I want to find the area underneath a curve, let me insert some rectangles and to help approximate the area. So for instance, here in figure 2, they're taking that area and they're drawing a typical rectangle in figure A. The rectangle would go from the bottom function to the top function, okay, and would have a width delta x, and the height would be the f of xi minus g of xi. That would be the height of the function, right? It would make, does that make sense? In figure 2a, the height of the rectangle is f of x minus g of x. Please let me know if you have any questions. Okay, and just good. All right, well, now in figure two, what they're doing is, you have a left limit A, a right limit B, and now they're adding more rectangles. And if you want to approximate the area between those two functions, look at the Riemann sum or look at the sum on top. So you add up the areas of the rectangles. Well, every rectangle, to find the area, you have a base and a height. The base is delta x, and the height is f of x minus g of x. And so that's how you get this sum above. Are there any questions on that? All right, well, if you're good on that, you know that, of course, if you let delta x become smaller, okay, and you take more and more rectangles. That means delta x would become smaller, and your number of rectangles, which is n, that's your number of rectangles you're using, n would go to infinity, and delta x naturally would have to get smaller and smaller, because as you take more and more rectangles, the width of the rectangles has to decrease. And so the area then would be the limit as n approaches infinity of this Riemann sum. That's what it would be. And the limit as n approaches infinity of a Riemann sum becomes, as you know, a definite integral. So if you're looking then to find the area, Okay, this is section 6.1. The area of a region bounded by curves. On the top would be your f of x function. On the bottom would be your g of x function. And then you're bounded on the left and the right by those vertical lines, x equals a and x equals b. Then the area of the function would be found using this integral. That's how you would find it. Okay, so and incidentally, if your bottom, if you're doing the area below a function and above the x-axis, the g of x function would equal 0. And that would just give you then your regular integral that you're used to doing. Okay, so are there any questions before we move forward here? All right, all right. Well, then let's go ahead and move forward. Let's go ahead and move forward here. So the book has good examples, and I'm content to look at these examples for the moment. So example 1 says find the area between two curves. All right, you have a region bounded above by the exponential function e to the x power and bounded below by the line y equals x, and then bounded on the sides by those vertical lines, x equals 0 and x equals 1. So if we want a picture of this situation, here we have a picture in figure 4. Okay, this is the area you're finding, that blue area. Okay, so are there any questions on figure 4? Okay. Well, then above, for figure 4, if we want to find this area, the area would be equal to the integral from 0 to 1, where your top function is the exponential function e to the x, and you subtract the bottom function x. And you integrate it, and you get the exact area, e minus 1.5. Okay? Give me a thumbs up if you're okay with that. Give me a thumbs up. Taj is good, wonderful. Ange and D'Angelo and Javier, excellent. Okay, all right. Well then I'll tell you what, and David's good, wonderful, wonderful. Well, all right, so let's now look at a second example. Okay. So now, well, hold on. Let's look at this second example. I've highlighted a few things, and that's fine. Here we want to find the area of the region enclosed by the parabolas y equals x squared and 2x minus x squared, okay, two parabolas. So, of course, we need to find limits. So we need to find where these two curves intersect. Okay, we need to, I mean, so what's this region look like? Well, if we go here to the figure 6, there's the region. And you can see the y equals 2x minus x squared. That's the top function. They call that y sub t. And then the bottom function is y equals x squared. They call that y sub b. The two functions will intersect at the origin at 1, 1. Okay, that's where those two functions intersect. So, you know, the intersection points, it's not hard, I think, to geometrically see that. But if we did it algebraically, which is sometimes necessary, here, sorry, here we solve the equation simultaneously. Okay, so if we set the two parabolas equal to each other, that means x squared equals 2x minus x squared, or 2x squared minus 2x equals 0. And we don't divide through by x. You know, you never divide by the variable. We're going to factor an x out, and we get 2x times x minus 1 equals 0. And so therefore, x would equal 0 or 1. And therefore, you know, when x is 0, you know, y equals x squared would equal 1. And when x is 1, the y equals x squared parabola would also equal 1. I mean, both parabolas will have the same y values. And so now you're basically now good to go. And there's your figure, and you're going to take the top function minus the bottom function and integrate that expression from 0 to 1. It's that simple. Okay, and so there I have it highlighted. So what they did was they took 2x minus x squared and subtracted x squared, and that's how they got 2x minus 2x squared. And they integrate it, and they get 1/3 as the area. Okay, are there any questions so far on this? Are there any questions?
Professor,
Yes,
how do you know which function go up and which function go down? Like, do you have to do the graph all the time?
You would have to graph them in Desmos or on your calculator. Yes, you would.
Okay.
Okay, all right.
I thought
And
it was
also, you know,
I thought
oh,
there
go
was an
ahead.
algebraic way to do it without doing the graph, but okay.
Well, you know, yeah, you in order to determine, I mean, the top and bottom function, usually you have to draw a graph. And you can see there that they're putting in, you know, vertical rectangles. They're drawing a vertical rectangle in figure 6 there, from the bottom function to the top function with a width of delta x. Now there's some importance to this, because okay, you have a situation where, okay, you're I want to say this the right way. You have a top and a bottom function, and you're putting in these vertical rectangles. But what if your functions weren't top and bottom functions? What if they were left and right functions? Well, let me show you how we would deal with that. So I need to get to figure 9, actually. Yeah, look at figure 9. So figure 9, you have an area, a blue area, but the function isn't bounded above and below by I'm sorry, the area is not bounded above and below by functions of x. The area is bounded on the left and the right by functions of y. Okay, that's what you have there. X equals g of y on the left, x equals f of y on the right. And then your limits are from c to d, but those limits are y limits. Okay, so you're used to dealing with x limits all the time. But you can have an area that has bounding functions instead of above and below, top and bottom functions. You have bounding functions on the left and the right. And so when you have this kind of situation, it really, the principle is the same. It's just you're using horizontal rectangles that have width delta y to them. And so the natural area formula would be the difference between the right and the left function, dy, the integral between the right and the left function, dy, where your limits go from c to d. Okay, are there any questions on that? Any
Professor,
questions? Oh, yes, D'Angelo.
is x r supposed to be like f of y?
X sub r means the x is a function of y, and it's the right function. So you see there in figure 9, you have, let me ask you there, in figure 9, what's the right function? The f of y or g of y?
The f of y.
F of y. So that would be that x sub r, you would put in f of y there.
Okay.
And then x sub l, the left function, would be g of y. So you would put in g of y.
Okay. Thank you.
Does that make sense?
Yeah.
Okay. Okay. Well, good, good, good. So, all right. Well, now we can look at another example here. We can look at another example, and this example is example 5. So you see, sometimes integrating with respect to one variable is easier than another variable. So they're saying sometimes integrating with respect to variable y is easier than with respect to variable x. So when you do integration, by default, you're used to integrating with respect to the x variable. But sometimes the y variable is easier. Okay, and so what we have here, is they want to find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Now what you'd have to do for that y squared equals 2x plus 6, I'll go to the whiteboard real quick. Y squared equals 2x plus 6. If we take the square root of both sides, you're going to get y equals plus or minus square root of 2x plus 6. So that means, like on I guess Desmos or your TI calculator, you'd have one function which would be positive square root of 2x plus 6. You would graph that function, and then you'd graph another function which would be negative square root of 2x plus 6. Okay, and if you graph those functions, you know, if you were to graph that, you would have something that looked like this. Okay, so this top function here would be the y equals plus square root of 2x plus 6. And the, you know, if you have like, if we were to draw an x and y axis here, this isn't exactly right. I'm sorry, hold on. This isn't exactly right. Let me do it fresh. Okay, now let me get the picture. So this would be y equals plus square root of 2x plus 6. This function here would be y equals negative square root of 2x plus 6, because the y values all along this red part, this red graph, are negative. The blue graph, the y values are all positive. And incidentally, this is an x and a y axis here. This x-intercept here would be negative 3, 0. Okay, and together, this entire graph, this whole graph together, would be the graph of the parabola y squared equals 2x plus 6. I'm showing you this because I want to go to the picture. I want to go to figure 12 in the book and show you that, well, I want to go to figure 11 and 12 in the book and show you the picture that for this particular problem. But are there any questions in terms of the what the graph looks like here? Because graphing is going to be critical for these problems. Not only do you have integration now, but you have graphing you have to do. Give me a thumbs up if you're okay. Let me know. Okay, thank you, Ange. Taja's good. D'Angelo. Okay. All right, well, now let me get back to the problem then. Okay, so here is figure 11. Now this figure, there is the parabola, y squared equals 2x plus 6. And what they're doing, I guess I'll mention this here. I'll mention this in the whiteboard. So y squared equals 2x plus 6. Okay, for this example 5 that we're looking at. If we wanted to solve that for x, we'd have y squared minus 6 over 2 equals x. Okay. So sometimes you know, an equation is an equation. And this equation here, y squared equals 2x plus 6, is the same equation as x equals y squared minus 6 over 2. They're the same, it'll give the same graph, same equation, okay? Just rewritten a little bit. Okay, also the line, you know, in this problem, for example 5, you have the line y equals x minus 1. Well, this means then that y plus 1 equals x. So again, both equations are the same equation. They both represent a line with slope 1 and y-intercept -1. But for our purposes, sometimes it's nice to rewrite the functions. So given that, let's go back to the example here. I want to go back to that figure. Okay, there's that figure. So they've graphed this parabola, this sideways parabola, y squared equals 2x plus 6, but they've rewritten it as x equals a half times y squared minus 3. And then the line, which is y equals x minus 1, they rewrote it as x equals y plus 1. So we have to decide, well, do we want to integrate with respect to x or y? And if we go here to figure 12, we'll come back to this figure 11. But look at figure 12. Okay. Now what they've done is they've just, you know, the parabola, they've written it as, you know, y equals, that sideways parabola, they've written as y equals plus or minus square root of 2x plus 6. And then the line is y equals x minus 1. So you see there in the picture what they're doing in figure 12. For some reason, they're taking the blue area and they're breaking it up into two areas, an area sub 1 and an area sub 2. Why would they be doing that? Why would they be doing that? What's different about the area A sub 1 and the area A sub 2? They're two different shapes. That's right, Jason. But why would they be why why not just have one blue area, same tone throughout the entire graph in figure 12? Well, Mario, we don't have quite a half circle there. That area A sub 1 isn't a half circle. It almost looks like one, but it's not, because good try there. And the area A sub 2 is not quite a triangle. But okay, now Taj has noticed something here. The area A sub 1 has an upper bound of square root of 2x plus 6. That's the top function. And the bottom function for bounding that area A sub 1 is y equals negative square root of 2x plus 6. But when you get to the area A sub 2, the top function is still y equals square root of 2x plus 6, but the bottom function changes into y equals x minus 1. You see that? In other words, if I wanted to integrate, if I wanted to find the total area here in figure 12 with respect to x, with respect to x, I want to say this the right way. One moment. Keep looking at it. Keep looking at it. Okay. If I wanted to integrate with respect to x, this would be how I'd have to do it. If I'm looking at for the area for that region, the area, this is figure 12. Figure 12, okay, in of example 5. The area would be equal to a sub 1 plus a sub 2, and the area of a sub 1 would be, the limits would go from -3 to -1. Top limit is the square root of 2x plus 6 minus the bottom limit of negative square root of 2x plus 6. Okay. Dx. And this is the top function y sub t and the bottom function y sub b. That would be area A sub 1. Now I'd like you to write this down on your papers. Area A sub 2, the top function is the square root of 2x plus 6. The bottom function is y equals x minus 1. And the x limits go from -1 to 5. So this is y top minus y bottom. Okay? Take a moment, write that down on your papers, because I'm going to go back to that figure 12, and now you're going to understand. You're going to understand a little better what's going on there. Give me a thumbs up when you have this written down on your paper. All right. Just give me, all right, give me a few thumbs up when you're ready, and I'll go back to that figure. All right, so who has this all copied down here? Thank you, Mario. Wonderful. Thank you, Ange. Jan, good. Thank you. All right, so now I'm going to go back to that figure. And so if you're going to integrate with respect to x, then in figure 12, that you'd have to find you have to add two integrals, one for area a sub 1, one for area a sub 2. And the two integrals are the ones I just showed you in the whiteboard. Now, that's a lot of work, right? That's a lot of work. Okay, if you're going to demand that you use top functions and bottom functions to bound your area, that's going to require two integrals. And they're not necessarily easy to do. That you can do them, but they're not necessarily easy, right? But there's an alternative. You don't have to integrate with respect to x. You could integrate with respect to y. And that's what they're showing in figure 11. Rather than looking at this blue area as a region bounded by functions above and below, let's look at this region as a region bounded by a function on the left and a function on the right. If you do it that way, the only bounding function on the left is that parabola, x equals a half y squared minus 3. Okay, that parabola is that's the equation of that sideways parabola. Okay, and then the line x equals y plus 1 is there. So you see, if you do it that way, if you integrate with respect to y instead of x, then you can get the answer very easily. And by the way, the limits, the y limits, you can see the bottommost point. Let me take this off. Hold on. One moment. In figure 11, the bottommost coordinate is -1, -2. So the bottom y limit is -2. The topmost point in the graph is 5, 4. So the biggest y limit is 4. And so here's your area then. The limits go from -2 to 4. Your right function is that line, x equals y plus 1. The right function is the line, x equals y plus 1. And the hold on, I have an idea. Let me not highlight this. Let me just shade it. Okay, that way I can have that and the figure together, and you can see both. Okay, so you see figure 11, you see the blue area, and you see above how they're calculating the blue area, where they're integrating with respect to y and using a left function and a right function. And the left function and the right functions are consistent throughout the entire area, so you don't need two integrals, you only need one. Okay, are there any questions on that? Any questions at all?
Professor,
Yes, Ann.
how important is it to find A and B, x equal A and x equal B, or y equal A or y equal B? Because they seem to have started by finding the point of the integral range before the actual.
Oh, I'm sorry. They do give intersection points there. Yeah, you need to find the points of intersection. You do need to find the points of intersection.
Okay.
So points of intersection are -1, -2, and 5, 4. So yeah, you can't do the problem without finding those points of intersection.
Right. Okay. Thank you, Professor.
All right, you're welcome. You're welcome. Does anybody want me to show you how they got those points of intersection? I can do that in the whiteboard if you need me to. Okay, let me do that. Let me go to the whiteboard. All right, no problem, no problem. So again, in Desmos, you can graph the two functions and I know like the TI-8384 calculator can find points of intersection between two curves. And but let's take a look here at, all right, so here are your two functions, and I want points of intersection. Okay, I want to find points of intersection. So what I'm going to do is I'm going to take my y squared equals x plus 6 and substitute in x minus 1. So x minus 1 squared equals x plus 6. Right? So you have to use both pieces of information. I'm substituting in y equals x minus 1 for the y in the second equation. And that's what I did here. Well, all right, x minus 1 squared is x minus 1 times x minus 1. That equals x plus 6. So I FOIL on the left and get x squared minus 2x plus 1. That equals x plus 6. So then, let's see, I can subtract x from both sides. And when I do that, I'm going to get x squared minus 3x plus 1 equals 6. And now I'll subtract 6 from both sides. Let me be a little bit careful here. One moment. Let me make sure I got everything correct here. Oh, I got an error here, class. I do have an error. This is a 2x, right? 2x, 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 2x. So I have to subtract a 2x from both sides. Okay, let me try it fresh. I want to try this fresh. I don't like mistakes like that. Let's try it again. I got a little bit sloppy there. You know what I need to do? I got y equals x minus 1, and I have y squared equals 2x plus 6. Equation 1, equation 2. I'm going to take from the first equation x minus 1 and substitute it in the second equation for the y. So that's then what I'm going to get is I'm going to get x minus 1 squared equals 2x plus 6. X minus 1 squared is x minus 1 times x minus 1. That equals 2x plus 6. So I'm going to get x squared minus 2x plus 1 equals 2x plus 6. I'm going to subtract 2x from both sides. Okay. This is going to give me x squared minus 4x plus 1 equals 6. Let me bring it up over here. X squared minus 4x plus 1 equals 6. Okay, now what I'll do is I'll subtract 6 from both sides of the equation. And that gets me x squared minus 4x minus 5 equals 0. Okay, and now what I can do is I can factor the left side as x minus 5 and x plus 1. And this implies that either x minus 5 equals 0 or x plus 1 equals 0. And so here x equals 5. Here x equals negative 1. And if we put like 5 in it, you like for x equals 5, you could put it in the first or second equation, but the first is easier. So y will equal x equals 5 minus 1. That means y equals 4. So you get the coordinate 5, 4. The second equation, y equals negative 1 minus 1. That equals negative 2. And so you'll get the coordinate negative 1, negative 2. So those are your points of intersection. Those are your 2 points of intersection, and those were the points of intersection that you saw in example 5 on figure 11. Okay, so this is probably about as hard as it would get in terms of finding points of intersection. Generally, I like to do them algebraically, but again, you can do graphs and find the intersection points that way too. Okay. So now, and this is in the recording, now if we go back to the, well, are there any questions on this? Any questions? Okay, very good. Thank you, Sandia. All right. All right, so now if we go back to the picture, this is where we were. So now does everything make sense here to this example 5? All right, good. Ange is good. Okay. Hold on here. Somebody else chatted something. I'm sorry I missed that. Let me see here. Taj is good. All right, good. So I'd like to look at an example of my own. Okay, I'd like to look at an example of my own. And let me give you a moment to copy this example down. Okay, take a moment and copy that example. Okay, so we want to find the area enclosed by the parabolas y equals 10x squared and y squared equals 10x. So what's the first thing for this problem that we need to do? What is the first thing we must do in this problem?
Yeah,
Find where they intersect.
Okay, and how, but even before finding where they intersect, I agree, Angie, even before that, what would be very, very helpful to have?
Something
So doing the
is a
graph.
success.
Doing the graph. That's right, everyone, doing the graph. Now, what I've done is I've gone to Desmos, and actually I've discovered really an amazing thing. Yes, Sandhya. So Desmos graphs, of course, you know, you're used to graphing y equals a function of x, but it'll graph y squared equals a 10th x. Let me go to Desmos and show you this. It's really pretty cool. Okay, so you see here, look at what we have here. Give me a thumbs up if you're seeing Desmos okay in the screen. Just good, good. Well, look there, y equals 10x squared. Thank you, everyone. I graphed that. And then y squared equals 1/10 x. I graphed that, and it gave me that blue sideways parabola. So like on a TI-83 or 84 calculator, what you'd have to do is you'd have to solve for y for that sideways parabola. And you'd have y equals plus or minus the square root of 1/10 x, and that's what you'd have to do to graph. But Desmos, you don't have to do that. You just type in the equation and you're good. So I think that's really, really nice, really, really nice. But the question is now, what's the area look like? What's the area look like between these two curves? Well, you know, the center of the action is clearly near the origin there. And what I have to do, it would be difficult using a TI-83 Sandhya, yes. It would be more difficult. What we're going to do is we're going to, you know, try to zoom in on this. So I'm going to hit the little plus sign here, okay, in Desmos. Okay, and maybe move the graph a little bit, and I'm going to keep zooming in. I mean, this is really, I can see why students like this Desmos. I mean, look at this. Look at what we are doing. We're hitting that little plus sign, and that zooms in. And how about that, class? How many are liking that? How many of you are liking that? All right, all right. I'm liking it too. And let's see about points of intersection. Now, I wonder if I can, if I click, I mean, what's one of the points of intersection clearly on the graph?
Zero,
I mean, it's pretty clear. Yeah, 0, 0. What's the other point of intersection?
0, 1, 0, 1.
Yeah, 0.1, 0.1. So, I mean, if I go to Desmos and click here, okay, look, see that? See that? 0, 0. Okay, and if I go to the other point, if I go to the other point in Desmos and click right there, look at that. How many now are not just liking Desmos? How many of you are loving Desmos? Based on there, the 2 points of intersection. I just clicked on them, and you know, I clicked judiciously, intelligently, but they're the 2 points of intersection. Yeah. So now, okay, so you know, I didn't have to algebraically find those 2 points of intersection. Yeah, so you know, and on the exam, you'll be able to do this as well. So what matters now is that area between the blue and the red graph. Okay, and we could integrate in this case with respect to x or y. It's not going to matter. Well, the 0, 0 is the vertex of the red of y equals 10x squared. But that doesn't really matter. It is the vertex of y equals 10x squared, but that doesn't really matter. What matters is that the origin is the intersection of the two parabolas, and so is the point a tenth and a tenth. And so now what we have to do is we have to find the area. And normally students will traditionally integrate with respect to x as opposed to y if they have a choice. In this case, I mean, if I go to the whiteboard here, I want to just show you something here. Okay, so if I look at this region. Okay, so this was the parabola there, the one parabola. This is the other parabola. Okay. Okay, and let me see. So I'm not even worried about the equations, but if we think about now, let me just see if I can maybe draw this. Yes, so Sandia, you'll have to, of course, the beginning of the lecture, we talked about finding the area, and this is all recorded. This here, this rectangle here has width delta x. So if I'm going to integrate with respect to y, or with respect to x, I would be inscribing horizontal rectangles. However, if I were, hold on. If I were to integrate with respect to y, I'd be using, no, I'm sorry, I'm saying this wrong. I'm saying this completely wrong. Hold on. Let me get this back here. This is, x-axis, y-axis. This width here is delta y. This width here is delta x. And for this particular solid, or I should say area, it's going to be equally easy to integrate with respect to x or y. It's not like the example 5 where it was much easier to integrate with respect to y than with respect to x, because the top, like if we integrate with respect to x, the top function here is consistent throughout the entire region. The bottom function is consistent throughout the entire region. There's one function on top, one function on the bottom. On the other hand, if we integrate with respect to y, the left function here is consistent throughout the entire region, and the right function here, that red function, is consistent throughout the entire region. There's one function on the left, one function on the right. So it doesn't matter. It'll be equal amount of work to integrate with respect to x or y. Now let me see. There was a question here. All right. So now let's go to the solution. I'm going to integrate with respect to x, okay, because that's what I'm used to, and it's just there's no. Now some problems you are going to have to integrate with respect to y, but this one we can integrate with respect to x and we'll be fine. So let me go here and find the problem again. Okay. So for our solution, okay, here here's that, here, you know, we're doing the solution now. I'm going to integrate with respect to x. So WRT is with respect to, okay? And here's the picture from Desmos. There's the origin, that's one intersection point. There's the 1/10, 1/10. And remember, y squared equals, no, hold on. The two curves, the two parabolas, one of them, right, was y equals 10x squared. And that's the bottom function, y sub b. The other function was y squared equals 1/10 x. And if we take the square root of both sides, we'll get y equals plus or minus the square root of 1/10 x. Okay, for that y, that second, hold on here, let me make it a little, hold on. So here's the 1. Here's the 1 function. 1 parabola is, let me get this better here. I don't like junk like that getting on my screen. Let's try it again. So y equals 10x squared. Check. There it is. Y equals 10x squared. The other parabola, you know, that's that bottom parabola, y sub b. The other parabola is y squared equals 1/10 x. Okay, x is in the numerator. So that means y would be plus or minus the square root of 1/10 x. Okay, but this graph here is entirely in the first quadrant. So that means you're going to choose the plus. And therefore, the top function is y sub t, is square root of 1/10 x. And this here is how you're going to find the area. So please let me know if you have any questions regarding that integral, because first you got to set up the integral correctly before you go to do your integration, right? In chapter 5 you were given integrals and you had to do your integration. Now you have to find the integral and then do your integration, so it's an extra step. But fortunately Desmos is helpful. All right, well, WebAssign wants exact values. It's not going to want decimals. So you got to integrate this. You got to integrate this carefully. So what I do is I say, okay, well, let's take a look at this square root of 1/10 x. I break that up as the square root of a tenth times the square root of x, which I can do. Because remember the rule, the square root of a times b is equal to the square root of a times the square root of b. Now, basically, it's just an integration problem. But I'm not going to round that square root of 1/10. I'm going to leave it. I'm going to leave the square root of 1/10 alone. Okay. How many have had issue? How many have had like in WebAssign, maybe when you round ahead of time and then WebAssign won't accept the answer because you rounded like a square root or something ahead of time, like a decimal, made it a decimal ahead of time, and then you didn't get an exact enough answer. How many have had that experience in WebAssign? Okay, Mario knows what I'm talking about. And really though, it's not a bad thing. WebAssign's teaching you a lesson. You keep the exactness in the problem until the end, and then you round. And it's no big deal. No big deal. Okay, so the antiderivative of x to the half is 2/3 times x to the 3/2. The antiderivative of 10x squared is 10 times x cubed over 3. Okay, and I'm down to this step, and I want to get this integral, and we'll take our break after I finish this problem. Yeah, so I've been going a little longer, but I didn't want to break the lesson up. You know, you're going to have some time to work a little bit on this, your next assignment here on section 6.1. But let's. Are we ready to go to the next page? All right, D'Angelo's ready to go. So, you know, putting in this 1/10 might seem, oh my gosh, you know, it's 1/10. I'm going to have to, you know, evaluate that, but it's no big deal. No big deal. All right, so I'll go to the next page then, and let's do the evaluation here. So I'm putting in the 1/10 for x, and I'm putting in the 0 for x. Naturally, this entire part here is equal to 0. And that leaves me with this expression here. Now I could type that all in WebAssign, and WebAssign would take that answer. But I don't really want to type all that in WebAssign. Maybe I can simplify a little bit. I think normally WebAssign, well, now if it says simplify your answer, then you might have to do what I'm doing here. But I think you want to do it anyway. So 1/10 to the 3/2 power is like 1/10 to the half power raised to the 3rd power. So 1/10 to the 3/2 power can be written as the square root of a 10th raised to a 3rd power. Well, the square root of a 10th times the square root of a 10th raised to the 3rd power would be, well, if I show a little work here, if I take the square root of a 10th, and I mean this, maybe I can do this here. Hold on. This part here is just the square root of a 10th to a 4th power, right? Well, that's just then going to be equal to well, I want to say it the right way. I guess I'll write it out. It'll be a root a 10th times square root a 10th times square root a 10th times square root a 10th. But that then is just going to give you the square root of 1 over 10 to the 4th power. See there? So I'm trying to show some of the little steps. Square root of 1 over 10 to the 4th power is just 1 over 10 squared. You work it out, and the exact answer is going to be 1 over 300. Right, the square root of 1 divided by 10,000th. That's exactly right, Sandhya. That's what this is. And that's going to be 100th, which is 1 over 10 squared. Exactly right. So these problems in section 6.1 are going to want exact answers. And of course, on the exam, section 6.1 is going to be on your going to be on your next exam, which is a week from today. And you know, you want to be doing these problems, you know, the right way, because you know, a decimal answer would be wrong for this problem. WebAssign and I want an exact answer, and you know, it's no big deal, right? No big deal to get an exact answer here. Are there any questions on this problem? All right. By the way, the area being 1 over 300, we would expect it to be a very small area, right? Because the intersection points for this our two parabolas are 0, 0, and a tenth and a tenth. So it's a very small piece of area. So we would expect the answer to be small, and it is. And yes, so this lecture is being recorded. This lecture is being recorded. So the recorded lectures are there in Blackboard. Absolutely. And also, it takes me a little time, but usually by the next day, I'll have the lecture moved over to, now occasionally I'm a little late on this, but I try to have the lectures under the course content too. Now this will be course content in chapter 6, right? But how many of you like to go to the course content to look at recorded lectures? How many like to go there? Because, okay, good. And those have the closed captions too on them. Does anybody use excellent. Does anybody use the closed captions? I'm just curious. Does anybody, you know, click on the CC for the closed captions? Probably isn't necessary, but okay, Ange, you do. Okay, all right. Well, great, great. Okay, well, let me stop the recording here. Very good.